Welcome to this explainer. Today, we are going on an incredible journey. We're starting from the familiar foundations of basic binary logic and diving straight into the absolute mind-bending mechanics of quantum computing. The entire digital world around us is built on a super simple concept: logic gates transforming bits of information. But when we step into the quantum realm, well, the rules of reality itself completely change, and so must our logic gates.
Okay, let's dive into this. We have a clear roadmap for our explainer today. First, we'll look at the limits of classical gates, and then the strict new rules of quantum logic. From there, we'll break down single-qubit gates, expand into multi-qubit gates and entanglement, explore the universal quantum gate sets that make programming possible, and finally, look at how these gates are actually built in the physical world.
All right, Section 1, the limits of classical gates. Let's talk about the bedrock of our digital world. So, let's start with where computing is today. Every smartphone, laptop, and supercomputer out there relies on classical logic gates, bridging the gap between raw bits and complex computation. But here's the thing, classical gates have a fundamental physical limit. Think about a standard classical AND gate. If you input a 0 and a 1, the output is 0. If you input a 1 and a 0, the output is also 0. Because multiple different inputs create the exact same output, information is fundamentally lost. It's irreversible. You can't just work backwards to find out what those original inputs were. And, according to Landauer's principle in physics, erasing this information inevitably dissipates heat. It's a hard limit. Quantum gates, on the other hand, are a whole different ballgame. To operate without collapsing their delicate quantum state, they have to preserve quantum information perfectly. They are strictly reversible.
Which brings us to Section 2, the rules of quantum logic, the strict fundamental rules that govern the quantum realm.
Let's look at the core laws that dictate how information is manipulated at the subatomic level. In quantum computing, every single gate must obey the principle of unitarity. Mathematically, this means quantum gates are described by unitary matrices. But what does that actually translate to in plain English? Basically, it means every quantum operation absolutely must be reversible. At any point in a quantum computation, you can theoretically apply the inverse of your operations, completely undo the computation, and return exactly to your original input. No information is ever destroyed. It's perfectly preserved.
Moving right along to Section 3, single-qubit gates explained. Let's look at how we mathematically and geometrically manipulate individual qubits.
So how do we actually manipulate these reversible quantum states? Well, we start with single-qubit gates, and this brilliantly illustrates exactly what we're talking about, the Bloch sphere. While a classical bit is stuck at either the north pole, representing 0, or the south pole, representing 1, a qubit can exist literally anywhere on the surface of this sphere. So, a quantum gate doesn't just act like a simple on and off switch. Instead, it performs a highly precise geometric rotation in a multidimensional space. The most basic of these geometric rotations are the Pauli gates. Think of the Pauli X gate as the closest thing we have to a classical NOT gate. It applies a 180-degree rotation around the x-axis of the Bloch sphere, effectively flipping a 0 to a 1 and a 1 to a 0. Super familiar, right? But because we are operating in 3D space, we also have the Pauli Y gate, which flips the state while adding a complex phase. And then there's the Pauli Z gate, which leaves the state's probability totally alone, but flips the phase of the qubit.
But honestly, perhaps the absolute most vital single-qubit gate is the Hadamard gate, or H gate. If you feed a definite state, like a 0, into a Hadamard gate, it maps it directly onto the equator of our Bloch sphere. What it does is create a perfect, equal superposition of 0 and 1. This right here is the true gateway to quantum computing. It's what allows quantum algorithms to process a massive blend of possibilities simultaneously, unlocking what we call quantum parallelism. It's a real game changer.
All right, now let's crank things up a notch for Section 4, multi-qubit gates and entanglement. This is where qubits interact to unlock true quantum power.
Because let's be real, a single qubit just sitting in superposition isn't going to outpace a supercomputer. We need these qubits to interact with each other. The absolute workhorse of multi-qubit interaction is the controlled NOT gate, or CNOT. This gate takes two qubits, a control and a target. The logic here is incredibly elegant. If the control qubit is a 0, the target qubit is left completely alone. But if the control qubit is a 1, the target qubit flips its state.
So the crucial point is what happens when we actually combine our gates. Imagine you pass a control qubit through a Hadamard gate first, putting it into a superposition of both 0 and 1, and then feed it into a CNOT gate. The target qubit now has to flip and not flip at the exact same time. This generates quantum entanglement. The state of one qubit becomes instantly correlated with the state of the other, no matter the physical distance between them. It is wild to think about.
We can even extend this logic to perfectly mimic classical computing right inside a quantum computer. Remember how we said earlier that classical gates lose information? Well, we solved that in quantum circuits using the Toffoli gate, also known as the CC0 gate. It uses 2 control qubits and 1 target qubit. The target only flips if both controls are 1. By setting the target to 1 initially, we can reversibly mimic a classical NAND gate, entirely without destroying any information or dissipating any heat. Best of both worlds.
Now we're moving into Section 5, Universal Quantum Gate Sets. It's time to start combining these individual building blocks.
With these single and multi-qubit building blocks, we are finally ready to assemble full quantum algorithms. But this brings up a massive question for computer scientists. Think about this for a second. Can we build any quantum program with just a handful of these gates? Because quantum states are continuous, there are basically an infinite, uncountable number of possible quantum gates. So do we need an infinite number of physical gates to build a computer?
Thankfully, the answer is no. But to understand exactly why, we have to divide our gates into 2 different camps. First, we have Clifford gates, which include the Hadamard, the phase gate, and that CNOT gate we just talked about. These are mathematically highly stable. They map Pauli operators to other Pauli operators, which makes them incredibly useful for tracking errors. But here's the catch. A circuit made only of Clifford gates can actually be efficiently simulated on a standard classical computer. So to get that true mind-bending quantum power, we need non-Clifford gates, like the T gate or the Toffoli gate. These break the mathematical symmetry and are exponentially hard for classical computers to simulate.
When you combine them, you get the Clifford plus T gate set. And this specific combination is what we call a universal gate set. Just like in classical computing, we really don't need infinite hardware variations. By chaining together just H, C0, and T gates, we can approximate literally any unitary operation, and therefore any quantum algorithm, to whatever level of accuracy we need. It's the whole shebang.
Okay, let's wrap things up with Section 6, Making Quantum Gates Physical. Time to bring all this abstract math back down to reality. We've spent a lot of time on matrices and abstract spheres so far. How do we actually build these mathematical matrices in the real world? Well, in a quantum computer, you are not going to find physical silicon logic gates connected by tiny copper wires. Instead, a quantum gate is literally an interaction between energy and matter. We physically implement these matrices using precisely timed bursts of energy, like lasers aimed at trapped ions or microwave pulses interacting with superconducting loops. These microwave bursts force the qubits to rotate in that multidimensional space we talked about. And finally, at the very end of the circuit, we apply a measurement gate. This permanently collapses that delicate superposition, forcing the qubits to choose a definite 0 or 1 so we can actually read the final answer.
Now, what's really interesting about this slide is the transmon qubit. It's an incredibly popular superconducting circuit, and it happens to be the leading approach for realizing these gates physically. It's a capacitively shunted Cooper pair box that relies on something called a Josephson junction, which allows the coherent tunneling of Cooper pairs of electrons. Leading companies and labs use these transmon architectures, bathed in microwaves at fractions of a degree above absolute 0, to string these gates together with absolute stunning fidelity.
Which leaves us with this final thought. By perfectly choreographing these reversible, unitary quantum logic gates, we are unlocking a completely new paradigm of computation. If a circuit containing just a few hundred clean, fully error-corrected qubits can theoretically perform more calculations simultaneously than there are atoms in the known universe, what scientific boundaries will we break next? It's an absolutely thrilling time to be learning about quantum logic. Thank you so much for joining me for this explainer.